Lecture 6, and the title is Applications of Lie algebras to solving PDEs. So, okay. So the first is linear homogeneous equations. Of order 1. Okay. So, so what would be an example with just one equation? Just give me one partial. No, I want to. Come on, guys. Partial. Okay. Let's write it general. This is a function of all the variables, partial by partial x1 plus a1 1n partial partial by partial xn. Sorry? क्या कह रहे? First order. Okay. So let's put a variable u here. Yeah. This is your first equation. Then a21 partial u by partial x1 plus a2n partial u by partial xn is equal to 0, and in general am1 partial u by partial x1 plus amn partial u by partial xn. So in the language of vector field, how will I write it? Let's call this the first a1 partial by partial x1 as x1, right? So as vector fields, this is the system. XIU is equal to 0. And XIU is equal to sigma Aij partial by partial xj. Okay. And I told you last time that if at some value, let's suppose that these commute. Okay. So if the field xi commutes, what does mean commute? Xi bracket xj is 0. If the field xi commute and xip for a point P, I varying from 1 up to m, are linearly independent, you can have you can find coordinates let's give them some name, x1 tilde, xn tilde, so that every xi, so that x1 is partial by partial x1 tilde and xm is equal to partial by partial x1 tilde. Okay. So what does your system now become? Partial f by partial x1 tilde is equal to partial u by partial, not u, let's say give it some u tilde, partial u tilde by partial x1 tilde equal to 0 and partial u tilde by partial xm tilde is equal to 0. So what's the solution of this system? Okay, let me write it again. So by change of notations, system becomes partial u by partial x1 is equal to 0 and partial u by partial xm is equal to 0. What is the solution of this equation? Any function which is independent of u, sorry? Not u is constant. Function which is independent of u1 up to, up to x1 up to xm. A function which is independent of x1, xm. Okay. So function, so solution u is equal to a function of xm plus 1 up to xm. This is a general solution. Now, these things occur a lot in Hamilton-Jacobi theory. You have commuting vector fields and you want to find out their common solutions. So even if you Google where do commuting vector fields occur, I tried it yesterday, I got so many things that I don't have time to explain to you. Okay. So it will give you a very nice applications to action angle variables and things like this. Okay. So this is, and now the surprising, here is number 2. Even if xi's don't commute, you look at the matrix of coefficient functions aij x1 up to xn. Okay. So and you take the reduced row echelon form. Okay. So if you use the reduced row echelon form, you will get some new fields and they will always commute and the solutions of the original system are the same as those. So every linear system, this can be reduced to a commuting system. It's very surprising, right? So then and I'll show this to you next time, because today I just want to do the last 2 lectures will be about applications of all this. So I want to just get all the definitions and concepts before I start doing that. Okay. So if reduce the look at the reduced of of the matrix it's an m rows and n columns, right? Okay. So, do you know what is the reduced row echelon form? It's something in linear algebra, right? But here we are using its reduced row echelon form over not constants but over functions, right? So what you do is you make the look at the okay. So briefly, reduced row echelon form, a matrix is a reduced row echelon form if it can be written after row operations and change and permutation of columns into an into an n cross m matrix, into n cross n plus k matrix, where the principal minor I, that's the identity matrix I n cross n. So okay, let me write this. So matrix is in reduced row echelon form. If after row operations and only permutations of columns, it becomes n cross n plus k matrix, where C ij varying from 1 up to n is the identity matrix. Okay, so this is how you check that whether matrix is in reduced row echelon form or not. And now the result is that so after you have reduced it to row echelon form, you look at let yi be the corresponding vector fields. Okay, then the solutions generic, because you have to of the original system are same as those of yi u is equal to 0. Okay. So in the next lecture I will give you an example. So I will look at the Lie algebra of the rotations. That's a highly known. What are the commutator? If I take I, j and k rotation around the z axis, y axis and x, y and z axis, no, it's the other way around anyway. So I bracket j is equal to k, j bracket k is equal to I, k bracket, so you want to find out the invariance of this. Now from physics we know that the invariant has only the fundamental invariant is the distance from the origin, but using this I will show you in the next lecture that this is what you get. Okay, and not only for this, it works for any group. I will give you an example of SL, maybe SL2 not SL2, SL2 is too trivial, SL3, okay, and the orthogonal group. So this is one thing. And now so this is given in so proof. You can look at this. I'll give you an archive link. Archive 111411.0091, and it's by myself, Biswas, Ghanam and Tahir Mustafa. Okay. I gave you archive because this is easy to access. The journal, I don't even remember what's the reference, but yeah, okay. I'm going to send all this to you. Don't you look at the, I send you notes regularly, you don't have to copy them, okay. And now the second is Laplace and wave equation in 2D. Okay. So what's the Laplace equation in 2D? Partial to u by partial x2 plus partial to u by partial y2 is equal to 0. And the wave partial to u minus c square partial to u by partial y2, right? Okay. So now in this in 2D these are trivial to solve. So trivial to solve. Why? Look at the operators. d2 by dx2 plus d2 by dy2. What is the factorization? d by dx plus I d by dy times d by dx minus I d by dy. That's the first one. And for the second one, minus, what is the factorization? D by dx plus c d by dy times d by dx minus c d by dy. This is the factorization. So minus c d by dy. Okay. So now if I give you, if I give you this equation, if you have this equation, d by dx how will you solve this? What is the first one? Says that this is an independent of x tilde, right? Partial by partial. So this means partial f by partial y tilde is some function of, no, it's independent of x, of y tilde. So what about f? You integrate with respect to y tilde, and but what is the constant of integration? It's not a constant of integration, but it's a function of x tilde. So f is integral of fy tilde plus some function g of, okay. So how can we reduce it to, so see, I just have to find what are the canonical coordinates for this. Canonical coordinates means a function. So if I give you a vector field, right, in two variables, canonical coordinate would mean functions f and g, so that x f is 1 and x of g is 0. So can you give me a function when I apply to this I get 1? Isn't it x minus iota by 2? When you so find canonical for coordinates. For d by dx plus I d by dy. Okay. So here you can just guess it, right? So they are, I gave you a full procedure, but here you can do it directly. So they are, when I apply x plus iy, x, I think it should be x minus iy, right? When I apply x minus iy, what do I get to here? You get 1, so you get 1 plus 2, so divided by 2, right? And when I put x plus iy, when you apply this to this, you get 0, okay? So this in complex analysis, this is z by 2, and this one is z conjugate by 2. So every solution is a function of h z plus k z conjugate, right? So these will in general be complex solutions. If you want real, you should add to it its conjugate. It's conjugate. So you will get a sum of a harmonic. You will get a real part of a complex valued function. Okay. So and similarly, what are the canonical coordinates? For partial by partial x plus c partial by partial y, and partial by partial x minus c partial by partial y. Because c is a constant, these commute. So can you guess here? Z minus, no, we have to divide by something, right? So x coordinates for d by dx plus c d by dy are x plus 1 over c y times 1 over 2 and 1 over 2 x minus 1 over c x minus 1 over cy. Okay.
Incidentally, these are the characteristic curves also, that you talk for.
G.
These are the where the function doesn't vary.
Where the function doesn't vary. Yes, yes. Okay. So and the canonical coordinate for this is R 1 over 2 x minus 1 over cy and 1 over 2 x plus 1 over cy. Okay. So every solution would be function of so every solution is function of is of the form f x plus y over c plus g x minus y over c. Okay. So this is famous historically. It's called D'Alembert's solution, right? But this is only good for rectangular regions, right? If you have circular, then you have to use some other coordinates. So what coordinates you choose depends very much on where you want to solve this equation. Hello, wake up. Because otherwise I'll go to sleep also. So you can go out. I mean, this lecture is on YouTube, so it doesn't really matter. Okay.
I have a question.
Ji.
So if somebody has the prior knowledge that you are dealing with parabolic PDEs and hyperbolic PDEs here, then you know that why you see iota at one point. And
can we discuss it later? Otherwise, I will not be able to finish this. Okay.
I just wanted to know whether we can anticipate here that why we have different, solutions if we do not have prior knowledge of the classification of the PDEs. Over here, we are getting two different solutions, right? One is the complex, the other is real.
That is because of the factorization.
Yeah.
Ji.
Okay, so it boils down to the same thing.
It boils down.
Form of the original.
It boils down to form. But more important, I think, is when you practically is the shape of the domain. You choose these coordinates x y when it's a rectangular region. If it's some circular symmetry, you change polar coordinates, and then you factorize the equation. Okay. Okay. So while we were able to do this with common sense, the idea of the inventor of theory of Lie groups was that don't ask me how he got this. No, I think I know how he got this idea, because he wanted to generalize Galois theory of algebraic equations. So he said we must look at symmetries of the differential equation, determine them, and use the natural coordinates coming from there to reduce it. Okay. Now this word you will not understand at the moment, because I have not told you what is the symmetry of a differential equation, right? So to explain this, I have to introduce to you some concepts from calculus, and I think you have done them already, part of them in Parvez's course, and there is no harm in looking at them again. So okay, so this is the Jacobian and the chain rule. the chain rule and differential of a function. Okay. Okay. So this is the key calculation. So if f is a function from an open set of Rn to reals, say f is a function of differentiable, of course, x1 up to u is open in Rn. And I take any curve C and C from interval I into U is any curve. Then d by dt of f of Ct, we have done this many times. What was it? It is gradient of f at Ct dot C prime t. D by dt is gradient of f dot C prime t. Okay. Okay. Now take any point, P, and a tangent vector at that point. V at P. Okay. So here is P and here is your vector V. So what's the most obvious curve you can think about? It's just P plus T times V, right? Okay. So, but if you take any curve, so take any curve. Any curve C, take any curves C1, C2 defined on the interval minus epsilon epsilon with C1 0 equal to C2 0 equal to P and C1 prime 0 equal to C2 prime 0 is equal to V, and you compute this, then d by dt of C1t at t is equal to 0, what was it? It was gradient of f at p dot C1 prime t at t equal to 0, which was your vector V, right? C1 prime 0 is equal to C2 prime 0 is equal to V. So this is dot V, and d by dt C2t is again the same, right? Okay. क्या जी? d by dt C1t, huh? Yeah, but C1 prime t आप ये कह रहे हैं d by dt, oh yeah, sorry, yeah, d by dt f of C1t at t is equal to gradient of f dot v, right? And the f of C2t is equal to gradient of f at p dot v. Okay, no doubt you were looking with blank faces because it was nonsense, right? Okay, so you know, is this thing, so the function from tangent space to R defined by V goes to gradient of f at p dot v. Is it linear in V? If I replace V by V1 plus V2, do I get, and if I replace V by some lambda, lambda will be multiplied. So this is linear is a linear function on V. Answer? Is a linear function on okay. So we call it the differential of f at p. So we call it the differential of f at p and write it as df p. Okay. So so when you move from point to in vector fields, you get when you move from point to point, you get different vectors, right? Here you get different linear functions. So this is called a differential form of order 1, right? It's a field of linear functions. The other one was a field of vectors, it was a field of linear functions. It's dual to the, in some sense, if you have a metric, but we don't need that, okay? Okay. So now this differential concept can be generalized not simply to functions from open sets of Rn to R, but it can be generalized to any function. Okay, so and this is so this was a function from differential of a function. Now differential of a function. So now generalization. Okay, so let U be open in Rn and V in Rm be open. Okay. Let f be a function, of course, the differentiable function on U, differentiable. So it will be a function of f is a function of n variables. Let f be a function of U, function on U taking values in V. So how will F look like? F of x1 up to xn, it will have how many components? M components. Let's give them some names. F1, and then Fm, x1, and we play the same game. You take any curve, so take any curve, चॉक्स किधर चले गए? मेरे इसके नीचे यहीं पे से. Okay, take any curve C from an interval I to U. So Ct is some functions of t, x1 t, xn t. Okay, and you compute then d by dt of fct. When I plug in here, it will give you gradient of f1 at ct dot c prime t, right? This is gradient of f1 at ct dot c prime t. This is the first component. So, and what would be the last? F1 at Ct dot C prime T. Okay. Gradient of Fm. Did I note it by capital M? Yeah. Gradient of Fm at Ct dot C prime T. This is the last component. Okay. And so if C is defined from on an interval minus epsilon to epsilon 0, and C0 is equal to P, C prime 0 is V, is a tangent vector at P. So d by dt of f of Ct at t equal to 0. This is gradient of f1 at p dot v, and the last one will be gradient of f m at p dot v. Okay. So we can see V was a vector in Rn, and this is a vector in Rm, and it's a linear. It's linear in V, right? So we should be able to write it also as a matrix. So what is the matrix? Would be actually what we call the Jacobian. Okay. So this is the same as partial f1 by partial x1 at p, partial f1 by partial xn at p, and the last will be partial fm by partial xm x1 at p, partial Fm, oh, shall F, I should, capital N, partial xn at P, and then apply to let's call the components of V V1 okay, where V is okay. So you see again, does it depend on the if I take any other curve which passes through the same point and which has the same velocity, which is the same tangent? The answer does not depend on that. Okay. So we call this function the differential of, we call the function which from T PU to T FPV defined by V goes to d by dt at t is equal to 0 f of ct, the differential of f at P, okay, where C is any curve with C0 equal to P and C prime 0 equal to V, okay, and we denote it by dfp. So this will be a map from the tangent space to P to tangent space at the image point, right? When you look at f of ct, what is the value of f of ct at t equal to 0 is f of p, right? So f of ct is a curve passing through the point f of p, and then really what we computed out is really a tangent vector at the image point, okay? So why did we not stick to the Jacobian? What was the need of this epsilon? It's exactly that you can now do calculus on any, if I give you any like sphere or a parabola or so, these things are determined in terms of curves lying on the surface or on the hypersurface, whatever you have, or in more technical language, you can do it on manifolds, right? Because a manifold is locally just like a piece of Euclidean space, okay? So for this reason we do it in this way, because it works for not just for flat surfaces but for everything, okay? And then here's the main result. This is a chain rule. So let f be a function from U to V. U is an open set in Rn and V is an open set in Rm, and G a function and G a function from V, which is open in Rm, to W, which is open in RL, okay? So I can talk about the composition, right? How do you compose these? F followed by G. So then F G composed with for F followed by G is a map from U to W, and the chain rule differential of G composed with F at a point P applied to a tangent vector V is equal to differential of G at Fp applied to differential of F at P, differential of or removing V, we have differential of d G composed with F at a point P is equal to differential of G at Fp composed with differential of F at P. Okay. I'm not going to prove it. I think you will understand many things if you do it yourself. Don't go to Jacobians. Use the definition how you compute differential by taking a curve, right? And if you do it, this will come out very easily. Okay. So surprisingly, this is this is very this is the key to many things, to almost all properties of vector fields. Okay. So then I need to introduce to you the push the push for, no, I'm not going to do pullback because I did not do differential forms, but because I don't need them right now. Okay, you need them for when you do integration theory. Okay, for differentiation you stick with differential operators. Okay, so now this is a very important concept. This is how many items did I got? Push forward of functions and vector fields. Okay. So let U, this time they are U and V be open set both in Rn. Okay, you take okay, let phi from U to its image be 1 to 1 and on to 1 to 1 and on to. Okay, and of course differentiable, because throughout we are talking about differentiable functions. So let f be a function on U. How can I define a function on V? F be a real valued function. So look at the here is U and this is phi U, and f is a function from U to reals. So what should I do this? I should take its inverse and compose by f, right? Then f then f inverse, oh no, not f inverse, phi inverse composed with f is a function on phi u, which is of course equal to v, and we write this as f as phi lower star f. Okay. Okay, and so let me give you in some sense trivial example, but in another sense the most important example. So example, take U an open set in R2. Okay, let f be the function f defined from U f of x y. No, f was the function phi of x y is equal to x plus a y. Okay, and f any function okay. So what is phi star of f? Phi lower star f at a point x y. What is it? It will be phi. What is the inverse function of this? X goes to x plus a. Would be x minus a, right? So this is f of minus a and y. Okay. Okay. So completely trivial, but you will see it is in some sense the most important also. Okay, and then push forward of vector fields. Okay, so phi is a function from phi is 1 to 1 and on to and oh yeah, well, okay, and x a vector field okay. So phi star f phi lower star is vector field defined on the image given by, so if I have a point in V, First I pull it back, I compute phi inverse of P, and then I apply x at phi inverse of P, right? And then I take the differential, it will land me to a vector field at the point P. Okay, that's how we define it. Given by phi star x at a point P is equal to x at phi inverse P and differential of phi at phi inverse P. Okay, so let's again take the example. Let Z be any vector field why not on R2. So I can look at it in two ways, as differential operator or as functions, right? Every function defines a differential operator. So let's look at it as functions. So Z of xy, this is xi xy and eta xy. Okay, let phi be mapped from phi of xy is equal to x plus a and y. Okay, so what is phi star of z? Okay, so by definition phi star of z at a point xy is z at phi inverse times differential of phi at phi inverse xy. Okay, what is z at phi inverse xy? This is z of x minus a. So this will be xi of x minus a comma y xi of x minus a comma eta of x minus a and y. Now let's compute what is differential of phi at any point. So what is phi of xy? Is x minus a and y. What is its Jacobian? Jacobian जी कौन क्या कह रही है phi of x plus a comma phi of xy is equal to x plus a comma y. Yeah, thank you. Okay, so what is Jacobian? Take this is the first component, this is the second component. 1 0 0 1. So Jacobian of phi is equal to 1 0 0 1. So differential of phi at any point P is the identity map so therefore differential of phi at phi inverse xy so therefore differential of phi at phi inverse xy evaluated at z of xy, z of this was it's just the identity function, right? This is equal to xi of x minus a. And the other one would be xi of x minus a, xi of x minus a comma y, and eta of x minus a comma y, right? So in this case the differential is very easy, right? Okay. And how much time? I still have 20 minutes, right? Okay, very good. Okay. Okay. Example. Let psi t be the one parameter subgroup. Psi t of xy is equal to x plus t comma y. Okay. So what is the corresponding vector field defined by this? So what is d by dt of psi t xy? Yeah, differentiate. What do you get? 1 comma 0. You are differentiating only with respect to t. So this is 1 comma 0. So in particular d by dt at t is equal to 0 of psi t xy. This is a constant field, and this is as a differential operator partial by partial x. Okay. And so here's a small result. Proposition. I mean, it's almost trivial. If d by dt of at t is equal to 0, psi t f star f 0, then psi t star f is equal to f. Okay. So let's go back to psi t star or f at a point xy is equal to f x minus t. Okay. How do you calculate d by dt? Is you take the limit of psi t star f at point xy minus psi 0 star f at xy over t as t goes to 0, right? So therefore d by dt at t is equal to 0, psi t star f, this is limit as t goes to 0, f of x minus ty minus what is psi 0 is the identity maps minus f of xy 1 over t, and what is this? Huh? It's almost partial. Come on. What is changing here? If I wrote instead of t fx, I wrote fx plus h comma y minus fxy over 1 over h. What is the limit? Partial f by partial x. But because of minus t, it will be minus partial f by partial x. So this is minus partial f by partial x, right? And so we are given that this is 0. So what does it mean? F is just a function of y, right? Therefore fxy is just some function of, and psi t star of f at a point xy is equal to f x minus ty. This is equal to, because f is just a function of y, it would be g of y. Okay. So this means just by, if I know that this is called the Lie derivative, if the d by dt at t is equal to 0, psi t star f is 0, then this function is invariant under the one parameter subgroup. Okay. And remember, I showed you last time that any vector field away from its singularities can be, you can find coordinates so that it becomes partial by partial x, right? And since these things can be defined, are invariantly defined, if I have a vector field and I have its flow and I compute the derivative of f along its flow, if it is 0, then the function itself is invariant. Okay. And exactly the same proof example, if psi t xy is equal to x plus ty, then and zxy is, it's a vector field which I identify as functions, is xi xy eta xy, then limit st goes to 0, epsilon t star z minus z over t at the point. If you compute it out, this will be equal to minus partial by partial x z. Okay. And therefore, if the limit in if this limit is 0, if this is 0, then epsilon t star z is equal to z. Exactly the same proof. Okay. And since any vector field in suitable coordinates becomes partial by partial x, the same thing holds for general vector field. So you see, with such a simple idea, we got something quite involved. Okay. So okay, now I come to the main. What is a differential operator here? So differential operators. So if I take a vector field x, what kind of vector field do I get? If I take a vector field x, what kind of operator do I get? A linear operator. So if x is sigma ai partial by partial xi, okay, and y is equal to sigma bj partial by partial xj. J is equal to 1 to n. So, what is xyf? Y of f is a function, then x of y of also makes sense, right? So, let us compute it out. This is sigma ai partial by partial xi, and then sigma bj partial f by partial xj, right? And then you use the product rule for differentiation and you can write it down. So it will be an operator of order linear operator, but of order 2, okay. And now we can define so in general, a linear differential operator is an operator which is the sum of the form a I1 ik x I1 x ik, where these are vector field and these are functions, right, where a I1 ik are differentiable functions and x1 up to xk are vector fields. and xi1 okay. So the most important for us are the Laplace operator and the wave operator. Okay. So what is the Laplace operator then? Partial 2 by, in n variables, partial 2 by partial x1 partial x1 square plus all the way up to partial 2 by partial xn2, okay, and similarly for the wave operator. Now, so now formulas for if x, y are vector fields, what was the definition of x bracket y of a function f? What was it? X y f minus y of x f. So what is x of what is x y f? Bring it to the other side. Would be x minus plus, okay, and therefore we can extend the action of the Lie algebra to operator to partial derivative. Therefore, x of, for example, partial by partial x of u by this formula, what is it? Instead of y, I have put partial by partial x. So what is it? Is it not x bracket partial by partial x applied to u of u plus partial by partial x of x of u? Okay. So this is how you can extend the action of the of a given Lie algebra to differential operators, and you can talk about the differential operators being invariant or not. Okay. So Dr. Vikas, this is independent of theory of prolongations. See, we didn't use any prolongation here, right? But yes, you can do it. So these are the basic formulas which we will use all the time. You don't have to. We have to go into jet space and so on, but you can do it.
Jet space.
J.
The jets. Some jets.
No. For this elementary thing, you don't really need it. You can do everything by using this formula. Yeah. See?
Yeah.
Okay. I've defined the action of x of a vector field on. And then from here you can define the action on any higher variable, right? Isn't it? Because the higher would be again things like this: partial 2 by partial x2, x of partial 2 u by partial x partial y. How would you, this is x of partial by partial x partial u by partial y, and then use this formula. You can extend it, okay, and then so these are the so this is so X is a vector field. F is a function. And phi is a one-to-one from open set of Rn to the same open set. So phi star phi this is the first formula. Then L x of f is equal to minus, but it doesn't matter, but the lead derivative is you take the flow of this and you define the let's say the one parameter subgroup was psi t, you look at psi t star f d by dt of psi t star f at t equal to 0, okay, and this is from the formula I gave you, this is minus xf, because the vector field in local coordinates away from singularity is partial by partial x. So this, and then Lx of y is equal to minus x bracket y, and Lx of Lx of yz would be Lx of y times z plus y times Lx of z, okay, and if x is a vector field, and psi t it's local flow, then psi t star if and only if the lead derivative with respect to x of d is 0, okay. So I'll give you references where you can use the detailed proofs, or yeah, I'll give you references, and then we will apply this to actually solving PDEs in the next lecture, okay. जी
सर ये जो आपने phi star of x लिखा है, सर इसको प्लीज आप एक्सप्लेन करो।
oh मैं समझ गया, आप phi star of g इसकी क्या डेफिनेशन है, g is any function, is g composed with phi inverse, ये था ना, right? So अब if f is a function, then x of f is also a function, right? And therefore you can talk about, okay, and if you go through the definitions, this will turn out to be exactly this formula. Okay. If you go through the definition, you will learn a lot. This is actually the main formula of the whole subject, although it's trivial to state, and also not trivial, but if you understand the definition, you will be able to do it. But by जी और इससे सबसे बड़ी बात जो इसका जो the main consequence is that phi star of x bracket y is the bracket of okay. So that's how you all of this comes from this basic formula. Yeah, okay. So what was the main idea? We said to prove many of these things, you can concentrate on field away from its singularities. From away from its singularities, you can straighten it out. You can find local fields, local coordinates in which x is partial by partial x. And then for this, its flow is very simple. Its flow is just you add xy is maps to x plus t comma y. Okay, and flow is very easy. The Jacobians of the transformations are very easy. So that's one way to do it. Okay. But where's your?
Yeah, I'm trying to relate this. So the lead derivative
G
L is with respect to a vector field,
is with respect to a vector field.
and you're taking the lead derivative with respect to V of, let's say, W.
G.
Okay. The way that I understand it physically is that you have a flow, you have a vector here W, which must be transported back to the starting point.
That's how
The difference of the two. But what is it? Is it the same thing as here?
it is exactly the same thing, but no parallel transport. Did you use parallel transport?
Well, that's how you would parallel transport a vector.
No, here. So x is a vector field, right? And so it has its flow. Okay. So you want to compute the lead derivative with respect to of y with respect to x? Y is a vector field.
Maybe we should discuss this in the discussion.
No, but let's just no because it's good for this rule. This is it not a vector field? I said if you have any one-to-one mapping, you can push forward. But now we have, because this is a diffeomorphism, it's in the same space, so it's a vector field in the same space, and then you can compute the and then limit at t equals to okay. Then it will. If you think of this as vector valued functions, it is clear.
It's very different notation that you're using, but it is the same thing. But why is there no metric in this space?
Because it is not essential. It is not essential. Metric will only come into play when you are talking about geodesics and volumes and things like this. क्या कह रहे हैं? डिस्टेंस का अगर नोशन आपको इस्तेमाल करना है तो आप जियोडेसिक्स इस्तेमाल कर आप मेट्रिक करेंगे, राइट? यहाँ पे कहीं भी नहीं इस्तेमाल हो रहा. यहाँ पे हमारा एम क्या है? टू स्टडी द एक्शन ऑफ ग्रुप्स ऑन डिफरेंशियल ऑपरेटर्स. This was Lee's idea, the originator of the theory of Lie groups. by studying the symmetries of the now we can talk about symmetries of differential operators. Before that we could not, right? Okay. So
sorry, forms वगैरह Rn में ही हम consider कर रहे हैं differential forms सब कुछ अभी तक Rn में ही हम consider कर रहे हैं
here everything is in Rn. When you have a manifold in local coordinate, it is in Rn, right? Because when you want to compute something, you have to give coordinates. Okay, so yeah, and when you want to assign a metric, you have to make sure that the definition is such that in different local coordinates they match up. Okay, I don't want to say too many things because you won't understand them. Because you don't, not that you are incapable, but because you don't have the background yet. Okay. Okay. चलें जी.